So the second thing is you need to have a good RF plan, okay, a radio frequency plan. So what is an RF plan? An RF plan is basically you try to map out or identify how your Wi-Fi signal will work based on the environment itself. So let's go back to the theoretical bits of Wi-Fi. Okay, as you can see here on the picture, this is a traditional Wi-Fi signal. Okay, it's called a waveform. Okay, it's an up and down signal. Now I won't go into the details of this one. We'll just go into a very brief overview. Okay, but this is typically how a Wi-Fi signal looks like. Okay, you can see it in the air, but this is how it looks like in terms of the technical stuff. Okay. Now, this is called the 2 hertz frequency. Right? Now, 5 hertz will be much more closer packed the signal. That's why you can pump much more speeds on those frequency. But most current Wi-Fi deployments right now are using these 2 wavelengths, 2.4 and 5 gigahertz. So another thing that you need to take into consideration when you're doing the RF plan is there's something called a free space path loss. Okay, so what does free space path loss mean? It basically means that whenever you're closer to the access point, you get a much more better signal, thus a better download and upload speed. But as you move away from your access point, okay, the signal becomes much more weaker. Thus, your speeds and the performance of your Wi-Fi actually becomes lower. Okay? So that's the meaning of free space path loss. The closer you are to the access point, the better you have, the better your Wi-Fi access is. The farther away you move from your access point, the slower and the more poorer the performance of your Wi-Fi signal is. Okay. Now, free space path loss has another name. It's called attenuation. Okay. Basically, attenuation happens because as your Wi-Fi signal leaves the access point and travels through the air, okay, its power becomes weaker and weaker as it travels farther out into the access point. Okay, that's why whenever you're away from the access points or very far away from the access points, you will actually see on your phone that you have a very low Wi-Fi signal. That's called attenuation. Okay. Now, in a perfect world, attenuation, okay, is something called gradual. Is performing on a gradual scale, as you can see here on the table. But in real life, attenuation is also affected by the environment itself. Okay, you have to remember that Wi-Fi signals also needs to pass through certain materials in your location or in your building or in your office. Okay, Wi-Fi signals tend to move very good through simple glass and tinted glass. Okay, they move very normal, okay, or there's a medium attenuation already whenever the Wi-Fi signal needs to travel through water or a brick. For example, I have at my back a brick wall. Okay, so if my Wi-Fi signal passes through this brick wall, there's medium attenuation that is already happening. It means your signal might become half. Okay, okay. The power becomes much more weaker after it has passed through the material. Okay? Now, there's a very high attenuation when it comes to concrete. Okay? So many of the buildings right now that's being built in your hometown or the material that is composed in your house is mostly concrete. That's why when you're using Wi-Fi signals in your house, there will be certain parts in your house that has a very weak low or a very weak Wi-Fi signal, and some parts of their house, okay, will have a very good Wi-Fi signal. Why is that? Because the material that your Wi-Fi signal passes through, okay, is different on each part of your house. Okay, so Wi-Fi signals tend to move very good through simple glass. Okay. Okay in terms of water and brick, and very poor in terms of concrete and metal. Okay. Drywall and ceramic, it's medium and high. Okay. What's drywall? Sometimes there's ceiling. It's called drywall. Sometimes your walls are also called drywall if it's something like it's composed of a wood type structure. Okay. Now ceramic is more. It's not really that used in terms of home construction or office construction, but it's there. Okay, it happens. Okay, it whenever Wi-Fi signal passes through ceramic, okay, it's passing through at a very poor performance. So there are two types of RF plans that you can do. Okay, for a certain client. One is predictive, and the second is on location. Okay, so let's tackle first predictive. So predictive RF plan means you need to have a site survey and you need to have the building plans with you for you to be able to complete this one. Okay, so what predictive RF planning does is it tries to simulate how your Wi-Fi performance will actually work. Okay, in the environment that it's going to be deployed. Okay, so I will need to switch into my Wi-Fi application that I use very heavily whenever I'm designing Wi-Fi signals or Wi-Fi networks, and that is called Ekahau. Okay, so Ekahau is a uh, Wi-Fi design application and spectrum analyzer, and it's being used by large companies, including me. So let me just toggle to that screen. So this is Ekahau, right? And Ekahau is um, it's not a cheap application to have, okay, but it gets the job done. Okay, so let me show you how I do predictive RF plan. Okay, so a predictive RF plan needs to have two things: a site survey, okay, where you walk through their property and try to identify the materials that the property is composed of, and second is the building plan. So I have those two here, and I'm going to demo to you how to do a predictive uh, RF plan, because this is something that is not really taught in schools and in real life, because really the application is not that cheap. Okay, so um, so I have Ekahau already started up. So I'm going to load the building plan for the 5th floor. So let's just zoom in here. And as you can see, this is the floor plan of the building, okay, of the hotel, actually, the 5th floor. Now, since I've already done a site survey of the hotel, I know what the walls are composed of and what the material of the doors and the windows are composed of. So I can actually plot those materials here, okay, using the building's floor plan. So the first thing I usually do is I need to set the scale. So because you can see here, please set the scale. So we need to set the scale because we need certain access points. Okay, the strength of their signal can actually change. Okay, as uh, as uh, um, as they pass through certain materials. Okay, and they have a certain range. So, for example, a regular home access point has a very weak Wi-Fi signal because it's designed for home, while enterprise grade access points have a much higher power in terms of their antennas, so their signal travels much more farther. That's why we need to set a scale so that whatever access point I put in into the building's floor plan, okay, it will be correctly simulated. So as of the moment, I have a sample measurement here. So that's 162, so that's 1.62 meters. Okay, and now I have a scale. Now it's time to put in the materials. So as you can see here, I can actually simulate what this material is, the materials inside the floor plan is made of. Okay, so it can range from a bookshelf, cubicle, doors. You have hollow wood doors or solid wood doors. You also have elevator shafts, marble, shelves, types of walls. Is it a brick or a concrete? Then you also have windows. Is it interior or a thick window? Okay, so these materials have certain attenuation built into them, and Ekahau has already measured that one. Okay, and they do an approximate, not really the actual attenuation that these materials are composed of, but it's an approximate. Right, so let me just, so the first thing that we need to do is we need to simulate what the building materials are made of. So for this example, let's go with concrete, okay? Because the building's external walls are made of concrete. Okay, so let me just put it here. Okay, so those are concrete. And as you can see here, we have a window. So I have to put in a thick window because that is for the outside. Then I choose again concrete and try to lay it out here. Okay, so there. Let's just finish this part first. Room 501, 502, and 503. So let me just quickly put in the concrete walls for this one. Okay, so we have there, here, then we have concrete here. How do I know this is concrete? Because I've already done a site survey, okay, for this location. And I have taken note of all of the materials that is being used on the property. So that is the room. So right now we have a door here, 2 doors, so that will be wood. And what they used is solid wood. So let me just put that there. So let's just zoom in into this part so that you will see how it is being simulated. Okay, so I think that's enough. That's too close. So let's zoom out and adjust this window. Okay, so I know this is a door, so I need to simulate a wood here. Okay, so that's 2 doors made of wood, and this one is made of windows. Okay, so let me just do a concrete first. Wall concrete. There. And this one, I know this is a bookshelf or a cabinet for the hotel guests to leave their clothes in. So that is a very tall cabinet, and it affects also Wi-Fi signals. So the bed really isn't an attenuation because it's a very low furniture. Okay, so seats are also a very low furniture, but as you can see here, we also have posts. Okay, so we have a big post here for the building, and that will also affect your attenuation for your Wi-Fi signal. So we need to simulate also that one. So we're going to be using a wall concrete. So let me just apply it here. Okay, and this one. Okay, so that's good. And now let's try to simulate how it will affect my Wi-Fi signal if I put an access point on the various locations inside the room. Okay, so let me just choose Unify, but Ekahau has already preloaded specifications and the simulations for the large companies offering Wi-Fi solutions. So you have Juniper, Lancome, Cisco, Meraki, Meru, Netgear, Ruckus. But what we're looking for is Unify. So we're going to be putting in a Unify AC Pro. Okay, so AC, for example. So if I put the access point here, and let me just zoom out one more level there. So if I put that access point here in the middle of the room, it will actually tell you how your Wi-Fi signal will propagate through the property, okay, or throughout the room. As you can see, I have a window here. I haven't put actually the glass, so the Wi-Fi signal is actually going out. And as you can see, Wi-Fi signals also tend to bounce through this concrete post. Okay, but as it leaves through the wall going out into the corridor, you will see that the Wi-Fi signal actually becomes much more weaker. Okay, so let me put in a glass window here. Let's go with material, and we're going to be using a thick window, and we're going to be putting it here, and it will actually simulate for you the effect of attenuation for your access point. Okay, so let's try to move this access point outside. And as you can see, if we put the access point outside the corridor, you're getting a very weak Wi-Fi signal already inside the hotel room. Okay? And it's not actually covering parts of the bed already, which is a very, very bad idea for a hotel room, because the number one thing that hotel clients, okay, or hotel users really do inside their hotel rooms is do Wi-Fi. Okay? Wi-Fi is a very, very important aspect in terms of doing reviews for hotels. Okay, so if hotels, majority of the hotels that I have worked with have very bad reviews because of the Wi-Fi. Okay, so really Wi-Fi is very indispensable in today's world. So this is the effect of attenuation. Okay, attenuation is greatly affected by the environment, okay, and the building materials where your Wi-Fi is being deployed. Okay, so the reason this part is actually very green is because I haven't plotted yet the rest of the floor. Okay, and as you can see, with just doing this room, okay, it took us already a couple of minutes. Okay, so I will load a finalized version of this floor, okay, so that we will have a very accurate simulation of how our Wi-Fi access points will perform on this floor of the hotel. So let me just click on new here. Actually, we're going to be opening this floor. Okay, so I've already finished plotting in majority of the windows, the posts, the walls and such. So as you can see, I already have the windows plotted here. The concrete walls is also plotted. The walls here for the structural of the hotel is also plotted. The elevator shaft is already plotted. Okay, and other things like the cabinet and others. So I think I missed something here. There's should be a door here, so let's just add that one in. It's solid wood. It should be up again here. And then the rest of that one is concrete. Where's that? There, concrete. So let me just put this one in there. Okay, so I've already plotted that one, and let's do a simulation of our access point. How it will um, perform in this floor of the hotel. So we'll try to pick a generic. Let's go with the generic home access point. Okay. So if we put one here inside for example, beside the TV of the hotel room, you will now actually see the performance of the Wi-Fi signal. Okay. It has a very good coverage area inside the room itself, but if I try to move this one outside the room and put it in the hallway, okay, the performance is actually very poor in terms of the bed space inside the room. Okay. So what we're going to simulate right now is access points for ubiquity, okay, because I'm using a ubiquity solution. So I've already done this prior to the building being built, this RF survey. Actually, the hotel was only bare. It only had posts and no walls yet when I did this RF planning. And based from that RF plan, that's how I managed to identify how many access points I'm going to buy, where will be the location, and how will my structured cabling play out in terms of this project. So for this case, we will be putting the access point at the corridors here. Now, this is open below because as you can see in the picture of the hotel, oops, let's minimize this one. The middle part of the hotel is an open space, okay, as you can see here. So let's go back to our Ekahau. So if I put the access points in outside the rooms at the corridors, you will actually see that it's not performing that well, okay, in terms of when clients are inside the rooms. Okay, the Wi-Fi signal inside the room is very poor. So let's try to add more access points. Okay. As you can see, it has still very poor Wi-Fi signal in terms of the inside of the hotel rooms. So let's try to scroll this one down here. As you can see, room 508 has a very poor Wi-Fi signal inside of this one. Okay, inside of this room. Same also with room 510. So let's try to complete this one. Okay, let's put another access point here and another one here. Okay. So how many access points is that one already? That's 5. And as you can see, we do have some okay performance inside of this hotel rooms at the side, but towards the bottom rooms, we have a very poor Wi-Fi signal. So let's try to move this ones around and see what performance we can get. Okay. So even if I move this here, there's poor performance there at that part. Okay, so even if I put this here, still very poor performance inside the rooms itself. Okay, so this is how we do RF planning. Okay, predictive, because we try to predict how the Wi-Fi signals will actually perform in the environment itself. So what I did here for the solution is I actually placed the access points inside the rooms itself so that the customers of the hotel will have a very good Wi-Fi performance since they are very near the access point. Okay, there's a lesser attenuation. So let me. The Wi-Fi access points was actually put here at the study table, and as you can see, they have a very good Wi-Fi signal. Okay, for their mobile devices inside the room. Okay, so let me just put that one in. So all of these access points are AC Pro Unify AC in walls. So I'm just approximating their location. Okay, so it here, room 508, the access point is here. Room 509, it's here, the study table. Room 510, here. Then inside room 507, it's here. Room 508, it's here. Okay. Room 506, it's here. And let's just go up here. Room 504 is here at the study table. Okay. And we don't have any access points at the pantry utility room because those are non-critical areas. We do have one at the sales and marketing office. So I put it here. So as you can see, this has a very good Wi-Fi signal all around the building, except the elevator shaft, another elevator shaft here for the service elevator, and a dead zone here for going down the entrance of the stairs, okay, going to the other floors. You won't really need Wi-Fi signal on those locations because in actuality, on an average hotel, customers are just passing by the corridors. Okay, they mostly use their Wi-Fi devices inside their rooms or at the lobby or any recreational area. Okay, so I'm not putting any access points outside the corridors here because they will still have a very good Wi-Fi signal when they are walking or waiting at the elevator. So actually, I need to put another one at the elevator. Okay, so that if they're trying to wait for an elevator, okay, they can actually whip up their mobile device, okay, and use their Wi-Fi. Okay, so this is called an RF planning, and I have to do this for all of the levels of the hotel. Okay. Now, as you can see, we have many concrete walls and doors for this floor. Okay. So what we need to do is we have an area also in the hotel. It's a restaurant. Okay. It's on the 10th floor, I think. We can actually also simulate that one. Now, restaurants, okay, are easier to plan because there's actually no walls that are separating your users, not unlike here on the 5th floor where we have the individual rooms separating all of your Wi-Fi users. So let's try to open also. Yeah, before we go to the restaurant, I would just like to explain what does the 1 and the 36 mean here. Okay, that 1 and 36 is called the Wi-Fi channels, respectively for the 2.4 and 5 gigahertz. Now, I will be tackling this one on a separate video, but suffice to say, those channels are very important also when planning for your RF deployment. Okay, so I can also toggle also. I forgot to explain this one. I can also toggle between 2.4 and 5 gigahertz. So I can do it here. So for 5 gigahertz, this is the performance. As you can see, they will have a very good coverage for 5 gigahertz on all of the rooms. And if I only toggle 2.4, they also have a good Wi-Fi coverage. Right? So what's the difference between 2.4 and 5 gigahertz? I'll be explaining that one in a separate video, but suffice to say 2.4 gigahertz, it's slower, but travels through materials much more better, while 5 gigahertz, okay, gives you faster speeds on your Wi-Fi, but travels very poorly in terms of the materials inside your property. Okay, so that's a basic overview of the 2.4 and 5 gigahertz. I'll explain that one in a separate video. Now, why can I toggle 2.4 and 5 gigahertz? Because the UniFi AC Pro can transmit both at 2.4 and 5 gigahertz. Your regular Wi-Fi access points at home, if it's only 2.4 enabled, it means it can only transmit 2.4 the 2.4 waveform. And if it's an AC compatible access point, it means it can transmit 2.4 and 5 gigahertz at the same time. Okay. So with Ekahau, I can do channel optimization already. And as you can see, the channels have already changed for each individual Wi-Fi access points. Okay. And this gives me a very good coverage if I put the access points inside the hotel rooms instead of putting it outside the corridors. So let's try to go with the restaurant. So let's not save this one. We'll go with the 10th floor. And for the 10th floor, this is an open area restaurant. So there's very little environmental attenuation that is happening. There are lesser walls, and it's a very open space. So Wi-Fi signals would be performing much more better at these locations. So let me just center out our floor plan here, and we're still going to use UniFi's AC Pros as our simulation. So this one, okay. Now, if I put the access point here at the ceiling in the middle of the room, you will actually see that it's enough to cover majority of the restaurant already. Okay. Now, as you can see, there's a dead zone here because your waveform for your access point is actually being bounced out, okay, by this wall. So your signal is actually going here, then bouncing out here. Okay. Now, how do we fix this? We put another access point at this location. And that would serve those clients here. How about the restaurant? We actually put another one here. Okay. But it's not really enough, okay, to just plan for the coverage of the Wi-Fi signal. You also need to plan in terms of the capacity. Okay, so that's predictive. Okay, we'll go with on location. On location is basically we do this whenever the infrastructure is already built. For example, there's already an existing hotel that has an existing Wi-Fi solution that is requesting us to improve on their Wi-Fi signals because their customers are having issues connecting with their Wi-Fi. So what we do on an on-location RF planning is that we go around the hotel, all of the areas of the hotel, for example, then we do a wireless signal survey where we walk using a laptop or our mobile devices, and we actually measure, okay, for each location of the area, how strong the Wi-Fi signal is. For example, here, okay, you can actually measure the Wi-Fi signal for an individual location. Okay, so you can do that for 2.4 and 5 gigahertz. Okay, so that's called the on-location RF planning. But if the client really wants a brand new solution for the Wi-Fi, I use predictive, and I mostly use predictive.